Support for Lab Out Loud is provided by the National Science Teachers Association, now celebrating its 75th year of supporting science education. Find out more about what NSTA has to offer, like its upcoming national conference this April, at nsta.org. You're listening to the Lab Out Loud podcast, Science for the Classroom and Beyond. And in today's show, we're talking once again to astronomer Phil Plait. He's here to give us an update on the hunt for exoplanets, those planets outside of our solar system.
The most common planet that we're finding is what we call a super-Earth. It's twice as big or more, twice the diameter of Earth or bigger, up to about 4 times the size. This is the most common planet we're finding in the galaxy by far. For all of history, we've been in this solar system, and now the moment we start finding other ones, we realize that ours is weird compared to the other ones, and we don't understand everything about how it formed. That is a scientist's dream.
That's up next on this 200th episode of Lab Out Loud. But first, I'm your co-host, Dale Basler.
And I'm Brian Bartel. It's 200th episode, Dale.
I know. Just think about that.
Well, our podcast is entering into like a tween level right now because we're in 11 seasons. And really, if you count our stint with periodicity, our first year, you know, we've got a 12-year-old, Dale.
This is our 12th season, though.
It is our 12th season.
Yes, we are in our 12th season, Brian.
13th season. We have a teenager if you count periodicity.
If you count the original podcast. Yep.
Oh my gosh. Do you ever do that with your children? Like, are they really that? They're 12 years old. My kids are 12 years old, so I
do that with myself.
You do have a birthday coming up.
You start counting the years and things like that. Yeah, it's crazy to look back, and it's been a blast, and it's just been really, really rewarding for me. I don't know about you.
It has been very rewarding for me, and it's been fun because we get to talk to so many wonderful people, and we've made some friends along the way. We definitely have had. You and I are friends, and we enjoy this time together. Sometimes I think our wives are like, "Oh yeah, you're going to go down and do a podcast, huh?" Yeah,
yeah.
And is it just a way to escape from the family? I'm like, I got to deal with my other 12-year-old now. But it's been enjoyable in that sense. But I've learned a lot too, and we've said this multiple times that I am a chemistry biology person, and you are, physics and geology, but I've stretched myself to learn about other areas of science that I may not have in the past.
Yeah, same here. Well, if you are interested more about our podcast and you happen to be going to the NSTA National Conference coming up in St. Louis in April, we are going to be doing a session on Saturday. It'll be in the program. I think it's Saturday.
I believe it is.
We're going to be doing a session called Talking Science, and we might be doing a little bit of a recording there and kind of talking about the benefits and what we've learned from all of this, and also sort of things that you could use in the classroom for podcasts. Brian and I have both dabbled in that in the past.
So we hope to see you in St. Louis in April.
Exactly. So 200th episode. Speaking of counting, our guest has been counting some things also. He's been with us all the way back in episode 12. It's Phil Plait.
Hi.
Welcome, Phil.
Just being friendly.
Welcome. For listeners who may not be familiar with you, tell us a little bit about yourself.
Well, my name is Phil Plait. I am an astronomer. I am more these days of a science communicator. I have a degree in astronomy, and I've done research astronomy, but over the years, I found that I like talking about it more. And so I write the Bad Astronomy blog for sci-fi.com, SYFY. Written a few books, do a few TV shows, that sort of thing. Just spreading the good word about the universe.
Well, we recently got a chance to see you spread some of that good word in person because you were in our hometown here in Appleton, Wisconsin, speaking at Lawrence University. Brian, that's your alma mater, right?
That is. I graduated from there, and they have a convocation series where they bring in guest speakers, and Phil was their most recent one. So it was nice to connect with him physically as well as over the air.
Yes, Phil, you did a wonderful talk about exoplanets, and maybe you can share with the listener some of the things you shared with us. Like, for example, tell us where it all began.
It is a new field. The first planets around other stars were only discovered in 1992. And
I was still in high school.
Yeah, well, I was older than that, but not too much older than that.
Not much.
The first planet around a star like the Sun was discovered in 95. Well, these were when they were announced, at least. And since then, we've discovered almost 4,000. And heaven knows we're so close to 4,000 as you know, you and I are talking here, that we may blow through that by the time this gets on the air. And so it is a new field, right? This is 30 years, call it plus or minus. But it's old enough to be established. So there's a lot of stuff we know. So there's a lot of good stuff to talk about. On the other hand, it's just gotten started. So there's tons of stuff we don't understand. Basically, everything that everybody's doing right now is breaking new ground. Even though we've got 4,000 of these things under our belt, we don't know that many things about them. It's remarkable we know anything at all. How big they are, how massive they are, what they're made of. But for some of them, we know a little bit about what's in their atmosphere because of a few little tricks we can do when we're studying them. But in general, it's like, is this thing habitable? We have no idea. Is there oxygen in its atmosphere? We don't know. So there's still a ton of stuff to learn. We're still surveying the sky. It's like we're still out there just, putting a mark in the column that says, yes, we found another planet. And it's getting to the point now where we can do what I call zoology, where we can start categorizing them and figure out what they're doing.
Can we compare the progress of what we're learning about these new planets to the progress of like other things in astronomy? Like where are we in the progress line?
Well, sure. I mean, you can always compare it to things like, I don't know, say stars. I mean, we didn't know that much about stars 150, 200 years ago. We knew that the sun was a star and that stars were far away, but we had to figure out how far away they were, and that took a long time, actually. That was really hard to do. Now we have a satellite in orbit. The European Space Agency has a satellite called Gaia, named after the Earth goddess, depending on how you want to say that. And that the job of that satellite is simply to measure the positions, distances, and colors of 1 billion stars, 1 billion with a B. It's doing it, and it's revolutionizing our understanding of how stars behave in our galaxy. I mean, we know there are stars like the sun and smaller stars, bigger stars. Some blow up, some don't. But how are they distributed in our galaxy? Did they form in our galaxy? Did they come from something else? Did they form near the center and move out? Did they form near the edge and move in? And so, we know a lot about stars, but there's still revolutions waiting to happen in our understanding of them. Even though that is an old established field. And I could say the same thing about galaxies. We know a lot about how a spiral galaxy works, how an elliptical galaxy works, different kinds of these objects. But, they form. What did they look like when they were young? What's their eventual fate? We don't know. With the study of exoplanets, these planets orbiting other stars, this is a brand new field. And so even though we're still, everything we learn about them is new, which is pretty cool, it's going to be hundreds of years before we have a really firm grasp about a lot of the stuff going on. We may be going and exploring these things, maybe not using starships, but in using probes that move at some fraction of the speed of light to scream through these other solar systems and learn what we can. And again, revolutionizing our understanding of them. The beauty of science is you can never sort of sit back and go, we now know everything about this. There's always going to be more stuff to know.
It's kind of, you mentioned like that taxonomy of planets that's coming into vogue now. I mean, and maybe there are like exoplanet astronomers on business cards and whatnot. What do you do for a living? Exoplanet astronomer. But what are some of these categories of planets that we're starting to see? Now we have 4,000. They're going to get sorted into different categories. What are they?
That's right. And that's the sort of the first thing you do in science when you have something new that you've discovered is you look for trends and characteristics. If you land on a new continent, say on Earth, and you just sort of making this up as I go along, and there are all these different kinds of animals there, and you say, well, some of them are large, some of them are small. That's fairly vague, but then you can say these have 4 legs and these have 6 legs. And maybe the six-legged ones are smaller than the four-legged ones. Why is that? And the more you can sort of categorize them, the more you can start to look for generalized trends. So then you figure out, well, the six-legged guys are a different class of animal than the four-legged ones, and so maybe they are super different in other ways. And you figure out that some are insects and some are mammals, and et cetera, et cetera. We do that with planets as well. The first planets discovered around another star were actually around a pulsar, which is a dead star, a star that blew up. And all that was left is this sort of super dense core of the star that is blasting out radiation, and is just a really evil place to be, and the last place you would expect to find planets. And yet it was the first place we found planets. The next planets that we discovered orbiting stars like the sun were more massive than Jupiter. And in our solar system, planets like that are really far out from the sun, very cold, take a decade or more to orbit the sun. The first ones of these found orbiting other stars were more massive than Jupiter and taking days to orbit their star. So they were so close in, they could circle around the star in a week. And they're super hot. So we call them hot Jupiters. And it's like, well, now wait a second. The first planets we find orbiting other stars like the sun are completely different than the planets orbiting our solar system. And so right away, we're learning something super important, that other stars make planets in different ways than we do. Or they make them the same way, but something happened later that, this planet formed really far out, like maybe Jupiter and Saturn did, but moved in closer to its star. Spoiler alert, that's what happened. And we're seeing big planets because they're easier to find. Smaller planets are tougher. So we've only found a few like the Earth, dozens, orbiting at different distances from their star. We don't know if they're habitable or not. Mm-hmm. And then what I think is the coolest thing is that as we discover thousands of these other planets, the most common planet that we're finding is what we call a super Earth. It's twice as big or more, twice the diameter of Earth or bigger, up to about 4 times the size. After that, it's more like Neptune, the gas giant in our solar system. So there's this gap of planets in our solar system between us and Neptune. There are no planets that we know of bigger than Earth and smaller than Neptune in our solar system. And yet this is the most common planet we're finding in the galaxy by far. So what's going on? Why don't we have one of these kind of planets, and why do other stars make them? We don't know. Lots of theories, but that's pretty interesting that we don't have that kind of planet.
Yeah, part of your talk was, is Earth special, and how we frame that question, and that whole part where is our solar system special, turns out it might be.
Yeah, maybe. Maybe not. Maybe we had super Earths. I didn't go into too much detail in the talk, and I've written about this on my blog. And I've got other talks where I do go into it a little bit more. But we may have had super Earths orbiting the sun. Mm-hmm. They may have been the first generation of planets orbiting the sun between the orbit, basically closer to the sun than Mercury's orbit is now. And it could be that those planets destabilized their orbits. They were affecting each other via their gravity. Jupiter kind of yanked on them. These planets collided, shattered. Most of that debris fell into the sun. Some of it was just blown out of the solar system, and sort of the leftover junk formed Mercury, Venus, Earth, and Mars. So the reason we have smaller planets in the solar system is that it's what was left over that could form planets. Most of that material went away. So we did have super Earths, but now they're gone. Maybe. That's a neat idea. The physics works out. It makes sense when you look at it, but we don't know if it's true. Just because it could have happened doesn't mean it did. Mm-hmm. But that is so cool to me that we have lived in our solar system all our lives, right? For all of history, we've been in this solar system. And now the moment we start finding other ones, we realize that ours is weird compared to the other ones, and we don't understand everything about how it formed. That is a scientist's dream.
You've mentioned a couple things about why some planets are hard to find, because they're too small, or the bigger ones are easier to find, and some of them are just far away. What are some of the challenges that we face in finding other planets, and how have we overcome some of those challenges to find our nearly 4,000? We've got 4K resolution now for planets.
Yeah, right. The big problem in a nutshell is that stars are big and bright and planets are small and dim. And in sort of every sense of those words, if you put a planet next to a star and you're just point your telescope at the star and say, can I see a planet there? The answer is almost always going to be no. The star is literally billions of times brighter than that planet. And the planet is so close to the star, they're both really far away. So even if a planet's orbiting the star far out, from our view, they look really close together. And the star just overwhelms the planet. Now, it turns out that's not always the case. There are a handful of planets we can see directly. There's a bunch of reasons for that that are complicated and technical. But in general, that's not a great way to look for planets. It's just too hard, at least with our current technology. And planets are small, and so they don't have as much gravity as the star. So as the planet orbits the star, the planet's gravity tugs on the star a little bit, and that velocity, that basically circular motion the star makes is detectable, but it's really hard. It's a very, very, very small detection, really very faint, very quiet. I can use a lot of adjectives like that, analogies, that makes it really hard to find a planet that way as well. The most successful method is what we call the transit method. And that's basically that if we see the planet orbiting the star, edge on, so that the orbit of the planet looks like a line moving back and forth as the planet circles the star. And that way the planet passes between us and the star, and it blocks a little bit of the star's light. So the star gets dim as the planet passes in front of it. You need to have a pretty big coincidence. That planet could be orbiting that star at any angle from our view. It just so happens we see it edge on, and it turns out it's not blocking that much light. I mean, Jupiter blocks 1% of the sun's light. So if you were some alien looking at our solar system. How do we know that? Well, because it's just a matter of area.
Oh, you just did the calculation. Okay.
Yeah, it's pi r squared. That's the area circle, right? So
I thought it was like for when you said it, I was like, how are we observing that?
Yeah. You don't have to. It turns out math lets you travel the universe without getting up from your room. In this case, Jupiter is 1/10 of the diameter of the sun, so its area is 1/100th. Area goes as the radius squared. So if the sun is 10 times wider than Jupiter, it's 100 times the area. Jupiter would block 1%, 1/100th of the sun. So if we are looking at a star like the sun and we see its light dip every year, say, by 1%, then we can say, a Jupiter-sized planet is orbiting that star, basically where the Earth orbits the sun, because it takes a year to go around. So you can tell by the dip how big the planet is. There are other things you can determine. They become very subtle and difficult to figure out. But if the planet, if you can measure how hard the planet's tugging on the star, you can determine its mass. So if you know its mass and you know its size, you get its density. Because that's all density is how much stuff you have in a certain volume. And the Earth, for example, has an average density of 5 times water. It's mostly rock and metal. Jupiter has a density of about water. It's mostly gas, but it's dense in the core. So Earth is 5 times denser than Jupiter. That's a huge jump. Yeah. So just by telling the density of a planet, you can sort of start finding out things about it, like what it's made of. And it gets more complicated from there. But the point is, it's not just we know a planet orbits there. It becomes we know that it has a density of this. That means its atmosphere may be like this. It's orbiting far enough from its star that it's cold, and we might be able to figure out what kind of orbit it has. So it's kind of amazing that without actually directly seeing these planets, we can learn a lot about them.
Yeah, I love you have essentially 3 different ways that you described the transit, and then the wobble. I forget what that's called. And
radial velocity, actually.
Yeah, the which is good Newton's third law kind of demonstration. Star, planet, planet on star.
I would like to take a moment and apologize for any students who are going to have to do math from this episode.
And then
I hear some density and some.
The other one was direct images, right?
Yeah, so we do have pictures of some planets orbiting other stars. Typically, these are very young. I mentioned that it's complicated earlier. These are young stars, so they're still very hot. young planets. Well, the star is young too.
Yeah.
But when a planet is young and it's just formed, it's still really hot. Basically, you're forming it by slamming asteroids together. That releases a lot of heat. And that's why the Earth is still hot, why the core is still hot. It just takes a long time to lose that heat.
You showed us videos that literally showed, like, here it is, and later when it was observed, here's the planet now. And that was breathtaking.
Yeah, there's these planets that you look at them in the infrared because the star isn't typically as bright in the infrared, whereas the planet, because it's warm, is. So you kind of drop that 1,000,000,000 to 1 brightness ratio to a much more manageable, hundreds of thousands to 1. But we can actually deal with numbers like that. And so, yeah, you can see these planets directly.
Do they use the techniques together, like transit and the...
Yes.
No, okay. So they combine
so, yes,
them.
In fact, the transit method gives you the size of the planet by how much light it blocks from the star. The radial velocity method, the fact that it's tugging on the star is making a little circle, and that means sometimes it's moving toward you and sometimes it's moving away from you, and you can measure that as a Doppler shift in its light. That gives you the mass of the planet. So those together give you the density. If you... I don't want to get into too much detail because it is complex, but if this planet passes directly between you and the star, transits the star, some of the light from the star is going to pass through the atmosphere of that planet. And if it is, say, a hydrogen atmosphere, hydrogen absorbs certain colors of light. So instead of just seeing the starlight coming through you unblocked, certain colors are going to be gone from that starlight. And if you can measure that, you can figure out what's in the atmosphere of that planet.
I love that we're using the same techniques. I mean, we're building upon them, of course, but it's the same idea. How we looked at our own planet first, how we looked at the things in our own sky, and we take those and say, okay, well, we know how the model works here, and now we start to expand that and look beyond and go farther and farther with that, and just keeps building upon that. I absolutely. I mean, it works in a lot of fields. Geology is a good example of it too. But I just love that.
Well, think about it this way: you have a tool shed where you can walk into this tool shed, and there is a rake and a hammer and a screwdriver and a level and a shovel and all of these, sort of basic tools. With that and the correct material, wood, metal, whatever, brick, you can make a house, you can make another shed, you can make a building, you can make all these different things, a barn, a farm, all of these different structures you can make with the same basic tools and material. This is a double analogy. That's what the universe has done. The universe has taken basically hydrogen and helium and made everything you see. And it's used these tools of gravity and magnetism and light. And in the same sense, science is like a toolbox that way as well. You have the same tools in science. We have, we can measure how long it takes things to happen. We use telescopes, microscopes. In the case of geologists, they have the same sort of tools used to build a house. You got a hammer, that kind of thing. And you can apply them in different ways. It's just limited to your imagination. You apply them in different ways and learn about what's going on. So the same telescopes that astronomers were using, in this case, almost literally, you could take the same telescope that was used to discover, say, Pluto or Neptune, and stick a digital camera on the back of it and detect some of these planets orbiting other stars. I have a telescope sitting literally 2 feet away from me in my office, a brand name small telescope that you can buy for not a huge amount of money, relatively speaking, that you could use to measure the light from other stars and see these exoplanets. They were hiding in front of us in plain sight all this time. It was just... It's not that easy to find them. It's just that once you do find them, you can look back and go, oh, all we had to do was this. And as soon as that happened, the floodgates were opened.
Has that ever been done by an amateur astronomer?
Absolutely.
Oh, okay.
One of the first transiting planets, I'd have to think of which one it was, but I know that there was one, and it's a mouthful of letters and numbers. It's HD 209456, I may have that number wrong. That's what's sticking in my head. That was one of the first transiting exoplanets. We observed it with Hubble. I remember I was working on Hubble at the time on a camera, and even from the ground, that transit curve, that plot you make of how bright the star is a little rough. It's not perfect. And then we used Hubble, and it was like as smooth as a piece of glass. It was the most gorgeous plot. And then I saw that an amateur had done it as well. And they'd used a small telescope. It was from the ground. Their data was really ratty, but you could see it. There it was. And if that person spent a year, for example, observing it over and over again, they could have gotten much better data. You just basically keep adding to your observations,
Sure.
Smooth it out. But the point is, they found it. It's just phenomenal. You can do this with small telescopes from the ground. Incredible.
So now, what's on the horizon? What
Everything.
What might we find next? Well, are there things like right on the cusp of like, hey, we're going to see this, or obviously we don't know that yet, but what do you anticipate coming out in the next 10, 20 years?
Well, the discussion of life is another thing that we transitioned into.
We know a little bit, and here we're just talking about exoplanets. I'm not even talking about dark energy and that kind of stuff. Mm-hmm. But the Kepler Space Telescope, which was using the transit method, discovered thousands of these planets, is out of commission now. It ran out of fuel.
What was its fuel?
I honestly, I'd have to go back and read.
I don't know. I just assume you know that off the top of your head.
I want to say hydrazine, but a lot of these spacecraft, they stay pointing using really extremely heavy metal discs, flywheels that spin really rapidly, and you can spin them up or slow them down, and that rotates you. And you can use fuel to help yourself point. Kepler had 3 of those wheels, and then one of them broke down, and they had to start doing some really clever things to keep it pointed. The point here is that you have a finite lifetime. You have moving parts and basically a gas tank, and eventually those stop working. So they followed up with one called TESS, the Transiting Exoplanet Survey Satellite, and that is working right now, and it's going to find many, many thousands of planets. And there are other more advanced, these are, I don't want to say advanced necessarily, but these are pretty straightforward satellites. They just stare at stars for a long time and look for dips in their light. And
now that we know the technique, it's not so hard to replicate that and mechanize that.
And once you know the technique, you can go back and say, I can make this a lot better. Yeah. So that's what Kepler and TESS, each time you do it, you make it more sophisticated, more clever. I'm not saying this is simple or easy or straightforward.
No.
Just that, you can write it down on a fortune cookie. How do you discover planets? You look for dips in light star. You point at a star for a long time. You just look at it. There are more sophisticated techniques we're looking into. James Webb Space Telescope will hone in on individual planets instead of just looking for them and find them. There are other techniques we can use to start mapping out these planets around other stars. Gaia was used to find a planet, some Gaia data, along with some ground-based data from years ago. There are a lot of different ways to do this, and the idea now is to find smaller and smaller planets so that our surveys are complete. So we look at a star and say, that has 6 planets bigger than Mercury, as opposed to 2 planets that are Jupiter-sized, to find smaller planets, to investigate their atmospheres better, and to look for signs of life. Basically, you look at this planet and say, there's oxygen in its atmosphere. That's unusual. We only, it's possible that that's due to geology, but it's also possible it's due to life. So, looking for life on these other planets, that's kind of where we're headed.
You described the habitable zone, and more importantly, explain the 3 little bears to me in a new way I've never thought about.
He was giggling.
A little social justice warrior action. The habitable zone of a star is a rough idea. It is not a definition. It is not anything more than a guideline. But the idea is that in this region, a certain distance from the star, a planet could have liquid water on its surface. So in sort of super vague terms, you want to be far enough from the star that your surface isn't boiling hot, literally, and not so far that it's frozen. And it turns out this depends on the kind of star you're orbiting, It depends on the planet. It depends on the atmosphere of the planet. The average temperature of the Earth is actually much colder than you'd think. It's actually, I want to say, 15 degrees Celsius, about 50 degrees Fahrenheit. Venus is a little bit closer, but it's much, much hotter than the Earth because of its thick carbon dioxide atmosphere. Mars has a very thin atmosphere, and so it's colder than the Earth because it's farther from the sun. But its thin atmosphere really makes that even colder. If you could swap Venus and Mars and give them a few million years, maybe more, and transfer 90% of Venus's atmosphere to Mars, we could have 3 habitable planets in our solar system. But that's a guideline, and the idea is that a lot of astronomers for a while called this the Goldilocks zone. The idea being that you're not too close, you're not too far, you're just right, and that to me is upsetting because that's the baby bear zone.
Yeah,
everything Baby Bear did was just right to Goldilocks, and Goldilocks was the one who was being too fussy. I don't like this one, I don't like that one, and it's like what we're learning in science is that the universe is smarter than we are. It makes things work in ways that we wouldn't have thought of. So you shouldn't just dismiss something just because it seems like it's too hot or too cold in the first place. And the other reason it upsets me is just because, it's a very colonial attitude. Here is a white European person wandering out in somebody else's territory, walks up to their property, breaks in, throws out the stuff she doesn't like and steals the stuff she does. I think that's a really great metaphor for how a lot of civilization, quote unquote, for the past few thousand years has worked.
Well, it's so funny because the Goldilocks thing you hear so many times, and I've never even dawned on me that it was never Goldilocks. It was Baby Bear was in the middle. Yeah. I mean, that was perfect. And Goldilocks could have took Mama Bear and Papa Bear's porridge and mixed them and would have been fine.
Hello?
Yeah. And more porridge.
Or just waited a couple of minutes for Papa Bear's porridge. And who makes porridge? And not that the bears are blameless here. Who makes porridge, sticks it on the table, and then just walks away? What happened out in the woods?
I think
Nest. I know what a bear does in the woods.
Nest cameras. I think the doorbell system. I see a commercial, a future Three Bears commercial with Goldilocks at the door.
Oh, that's
my cats would have ate the porridge if we just left it on the counter and went out in the woods. But
that is such a great idea, and it could just end with them eating. and it's like you're not really clear what they're eating. It doesn't look like porridge they're eating. Why would you need a fork and knife with porridge?
Mama Bear pulls out the phone and says, "Hey, get out of my yard."
Yeah, there's a movie that ends with a little bit of cannibalism. It's a satire. And at the end, they wind up eating somebody to stay alive, and and somebody says, "Yes, she was a woman of, you could say, good taste." No, that always makes me laugh.
Well, I'm actually glad you brought a movie reference in there because one of the things that happened besides science questions were science fiction questions from the audience when we attended your talk there. Now you kind of invited that. Yeah, you invited some of that there. So I mean, you took a hit on the spore drive, which is absolutely deserved. So because of course, if they had the spore drive, then the whole episode or the whole series of Voyager just doesn't make sense. But never mind.
They're going to have to explain that in Star Trek Discovery why, if it becomes forbidden knowledge, or it breaks down in a way that they decide, there's a general order 0. You may not use the mycelium network or whatever, the mythelial network. We'll see.
Yeah, it's
very curious I know we're off the rails here, but my biggest hope.
We're talking first season Star Trek Discovery, just for anybody who's in the
new
dark
show. It's on CBS.
It's on the second series now.
Mm-hmm.
Yeah, and it's on the second season. My biggest hope for this show, basically, is that they are given plenty of notice before it's canceled, or they basically say this is the last season. So many shows, Star Trek Enterprise was cut off, Stargate Universe was cut off.
Mm-hmm.
Oh, don't get me started on that one.
I know, and I would love, when writers know that they've got, you're wrapping this up and you've got a year to do it. You get a show like 12 Monkeys. Which they could see that coming a long way off, and basically generated the episodes in such a way that when it ended, you're like, that was satisfying. They answered all my questions. We're done. I don't need to have a movie or anything to go back and explore things because it's all this perfectly wrapped story.
So not Firefly.
So I want Discovery and have it handed off to the next, you know.
Not Firefly, but Agents of S.H.I.E.L.D. kind of did that. But
Yeah.
But one of the questions that I did have is like, realizing that, of course, we're talking about science fiction, heavy emphasis on the fiction. What science fiction gets it right more in your opinion? Like, you know, there's some things that come to mind in my head. The Expanse, I feel like
The Expanse is the answer. Yes.
Gets it right. I mean, yeah, we've got this future where we are still limited to our solar system, but, you know, they capture the physics of it, but still, you know, we can imagine a future of that. And that's still that science fiction part of it, but they still adhere to the scientific principles and instead of like, you know, invoking a spore drive kind of a thing. What else out there do you like that, you know, it could be any type of media, books, genres or whatnot?
Well, in my view, there are two ways to look at your question. One is that which one gets the science right as much as we know today? And the other one would be, you know, let's imagine faster than light travel, time travel, artificial gravity, transporter technology, whatever you want. Then the question becomes, if I accept the premise of this, is the show or whatever, is the story internally consistent? And that's where I kind of start to draw the line, because look, you have The Expanse, which takes place, like you said, in our solar system. The only sort of far out technology that humans have are fusion drive spaceships, basically ships that can accelerate at huge rates so that it doesn't take 10 years to get to Jupiter. It takes a couple of weeks or, you know, a month or something like that. And internal to the show, well, The Expanse wins on both counts because the science it uses is basically correct and, in fact, is important to the show. There are battle scenes where they stick to the science, and what they do is correct, and it makes it more exciting and more fun to me. And where they do have, I don't want to give any spoilers, although, you know, by the end of the first season, it's pretty clear that there's going to be some weird stuff going on. Even the far out tech that you start to figure out is happening is still internally consistent. It's done correctly. There's a set of rules on how this stuff works, and they obey it. You know, and Star Trek is not great about that. You know, how fast is warp travel? Well, fast enough to get the Enterprise to wherever it needs to go for maximum drama. That's sort of how fast warp drive is. I love Star Trek. I love the storytelling, but it's not maybe the most internally consistent. But The Expanse is the best on that. The Expanse is so good when it comes to that sort of thing that when there is an error, something, you know, it's like, oh, that, you know, they clearly couldn't have filmed that the right way, or they needed to do this because otherwise this doesn't work at all. This scene doesn't work at all. It stands out. Yeah. In Star Trek, you know, when it's like, why don't you all just use transporter technology to live forever? You just kind of go, okay, whatever, I accept that. But in the Expanse, it's like, oh, you know, wow, it really stands out when they make a mistake. And that's great because they are so good that 99 point whatever % of the time, it's right on the money.
See, that's what bums me out sometimes about like these discoveries about exoplanets is we're going to learn all these things and then there's going to be this huge time period where we'll just know it's out there and out of our grasp. That bums me out.
Well, that's science, right?
I mean, can't get there.
That's been true forever. I mean, we've known about Mars since antiquity.
Yeah, I guess I had the luxury of looking back in time, so it goes faster.
Yeah,
through a history book.
And so, you know, imagine not even knowing anything about Mars. When I was a kid,
nor have we traveled to the core of the Earth. And there's other movies that we can invoke there, but never mind.
Yes, that is true. But as a kid, I would watch these movies where astronauts would go to Venus, and it was a swamp planet, or it was run by women. Yeah. You know, because it's Venus, so of course it's run by women. And this was all gee whiz stuff when I was a kid. And you know, then we find out that it's actually hot enough to melt zinc on the surface, and that kind of sucked. But you know, for a long time, we had no idea what was going on Venus, and to actually sort of kind of have technology that's advanced enough that you'd think you could, but still not. You know, we have space travel, but we still don't know what's under those clouds. That's super frustrating.
Yeah.
And now we've got a taste of Titan, the largest moon of Saturn. And using radar mapping and a lander, actually, the Cassini mission, mapped the surface. We know there are lakes of liquid methane on Titan. It has a liquid cycle. We have the water cycle on Earth where you have, evaporation, which makes clouds and rain, and then that flows down or snows down. And on Titan, you have the same thing. It's just with methane. But that's all we really know. We don't have close-up pictures. We don't know in detail what that's like, and that's super frustrating.
Just imagine methane snow days.
Yeah.
We have a snow day right now, listeners. It's nice.
It's snowing as I'm looking out my window.
Be a
only
different
a
kind of snow blow? No, probably not. We talk about life and searching for it by looking for the presence of water. And I think modeling it after the life that we know of, is that the science, or is that just us going with what we're familiar with?
Oh, you go where the light's good.
Okay.
It's if everything is dark except for one spot that's lit up, and you're looking for something, maybe you should start there. That's just because it's the easiest. Get it out of the way first. And so, when you're looking for life, everywhere we look on Earth, it's based on water, one way or another. There are some brands, some flavors of animals that, or plants or whatever types of life on Earth that don't need as much water as others, but they probably all evolved from something that did, and over time relied less or more on water. So just from that principle, it makes sense to look for water on other planets, because that's the easiest thing to look for and to see if life could be supported there. But there's also physics and chemistry. Water is a super simple molecule to make. It's just an oxygen atom with two hydrogens stuck onto it. Those are both very common in the universe. And in fact, every place we look in the solar system, we see water. Even Mercury, and to a much lower extent Venus, there is water there, frozen in the poles of Mercury in deep craters that never see sunlight, even though most of the planet's super hot. Parts of it are very cold. And we look at the moons of the outer worlds. Europa around Jupiter is the most famous one, and Enceladus around Saturn. But honestly, almost all of them have ice on them, water ice. Asteroids have water ice. Comets have water ice. Everywhere we look. And then if you look at other stars, we see it there. We see water in gas clouds that are forming planets. And we just know that water's everywhere. If water is the basis of life on Earth and water is everywhere, water is where the light is good. That's why we look for water. It's the most obvious place to look for signs of life.
So it's not just us looking for the life we know. The element, what we know about the elements, let's say the periodic table essentially is also driving the discussion.
Yes.
Sort of like that's why carbon's such an obvious candidate too, then. Yeah,
carbon... among all the elements, carbon is unique in that it can form long chains. Mm-hmm. It can connect with itself like Legos, more like an erector set, although those are, I don't know if those are around anymore. And so you can make really long molecules. And so you start to get really complex chemistry. And silicon is the usual example, silicon-based life in science fiction shows. But silicon doesn't do that as easily. It can kind of, sort of, but carbon. And in the universe, if you have something really hard to do and something that's really easy, chances are the really easy thing is the thing that's going to happen way more often. And so that's just, when we talk about carbon-based life and water, it's not a coincidence that that's why we're looking for that. It's not prejudice. It's like, no, The universe does this. And so this is the best place to look.
Okay.
Well, Phil, we've learned a lot, of course, in the last 40-some minutes there.
And 20 years.
And 20 plus years, yeah. So if you were to leave a message to the youth of today that might be in science and thinking about a science career, maybe in astronomy as well, what advice would you give to them right now?
Stay in school.
No pressure.
Don't do drugs unless you want to understand.
No jewels, kids.
Yeah, if you want to understand black holes, then absolutely do drugs. It's the only way to figure that out. That was a joke we had in grad school because there was actually a federal law or something that said you had to put anti-drug messages in all these government websites, and there was a NASA thing that says don't do drugs. It says funny. You want to study black holes, don't do drugs. No. the advice I would have is simply to maintain your sense of wonder. A lot of schooling, a lot of life, a lot of the internet, and a lot of other people are going to try to grind down your sense of wonder, your sense of awe, your sense of hope. All of these are essential to exploration in science. If you want to find that next planet, to discover that next universal law, or anything like that, you have to maintain, and not just a sense of wonder and awe, but your imagination. Don't let anybody say your imagination is silly. One thing we've learned about the universe is that it's more clever than we are. And stuff I used to sort of poo-poo when I'd watch it on TV when I was a kid. Oh, a planet with a green sky. Oh, a planet orbiting 2 stars. That's ridiculous. It would never work. And it's like, yeah, we're finding stuff like that all the time. The universe does that. Be open-minded, and that will serve you well over your life.
Well, fantastic. Thank you so much for your time, Phil. We look forward to having you on episode 400.
I'll be there.
Think of all the planets by then.
Yeah, that'd be great.
If you'd like to learn more about today's episode, head on over to our website, laboutloud.com, for more information. You can also find details about all the previous episodes, and you can leave us feedback and comments. We want to hear from you.
If you enjoyed the show, make sure you've subscribed on iTunes, Google Play Music, or your favorite podcasting platform. And if you really enjoyed it, consider leaving us a rating or a review. Your feedback helps others find our show.
If you like Lab Out Loud and you love the show that we provide for you, please consider supporting the show at our Patreon page. Head on over to patreon.com/laboutloud for more information. Until next time, I'm Dale Basler.
And I'm Brian Bartel.